Good day, students. Today we are going to look at electrolysis of molten lead to bromide. In my other sessions, I was just looking at the basics of electrolysis. Now, today we are just going to look at electrolysis of molten lead to bromide. Okay. Please remember that we are saying molten lead to bromide, meaning to say we have just taken the salt lead to bromide and we have just allowed it to melt. That's why it's molten. So if we are to look at it, it's just lead to bromide, okay? And we put the symbol L, okay? We have not dissolved it in water, okay? If we are talking of aqueous lead to bromide, we would have dissolved lead to bromide in water, but this is molten lead to bromide, okay? So we're just going to analyze what happens when we break down molten lead to bromide. Okay, I have a very simple diagram which I have put here on the whiteboard. Okay, so this is our molten lead to bromide, which is our electrolyte. Okay, and we have our power source here, which is negative this side and positive that side, and then negative this side. This is going to be our cathode, like we discussed in our previous session. And because this is positive that side, that is going to be our anode. Okay, now let us look at what is going to happen during this process, okay? And also, take note, in this type of electrolysis, one may ask, why do we need heat, okay? Remember, we are supposed to keep our lead to bromide in the molten state. One property of ionic substances is they will only conduct electricity only when they are in the molten state. Okay, so this heat here is meant to ensure that the ions, lead ions and bromide ions, are always mobile. Otherwise, if we remove heat, okay, our electrolyte will solidify, okay, and the process of electrolysis will actually stop. Okay, right. So it's important for us to have a source of heat here so that we have our electrolysis process happening continuously. Okay. Right, so whenever we are describing electrolysis, we are supposed to split the description into two parts, okay? We are supposed to look at what is going to happen by the cathode, okay? Let's analyze the cathode reaction, okay? What's going to happen at the cathode, okay? I'm just going to put that negative sign so that we'll always remind ourselves, okay? Right, in lead to bromide, we have two ions. Okay, so if I write down here ions present, okay, it's important in electrolysis for you to write ions present, especially when you are in the aqueous phase, okay, because you might have 4 ions present and then you have to deal with that selective discharge of ions. But in molten compounds, it's very easy. We have a binary compound which has been allowed to melt, so ions present, we are only going to have our lead ions, okay, and we are going to have our bromine ions, okay, right. So like we saw in the previous session, because the lead ions are positively charged, the lead ions will go to the cathode, okay, so the lead ions will go to this electrode. All right, now the cathode, okay, is negatively charged. It's a rich source of electrons. Okay, so what happens is each lead ion, when it arrives, okay, at the cathode, it's going to pick electrons. It's going to gain electrons equivalent to the charge. So it's +2, so it's going to gain 2 electrons, okay, and we'll have lead, okay, we'll have lead. And actually, as this process is happening, the cathode, you are going to have made a grayish deposit on the cathode, because lead ions will actually move from solutions and then they get deposited on the cathode. So there's that gain of electrons, okay, by the cathode. All right, let's look at what will happen by the anode. Okay, again, by the anode, I'm going to do that so that you remember what type of charge that you have. Okay, so this one you have to be a bit careful. Okay, we have bromide. Okay, there are 2 ways of illustrating this equation. You might say, The bromide has an excess of electrons. So here, when it gets to the anode, which is positively charged, okay, each bromide ion is going to lose an electron, okay, and then we're going to have bromine gas. This is the most important part. Bromine gas is diatomic, okay, so we need to balance the equation, okay. We put a 2 here and then 2 electrons like that, okay, so that the equation is balanced. Let me just correct something here. Minus 2 electrons, okay? That's one way of writing it, okay? Some textbooks would illustrate it as 2Br minus, and then you have Br2 gas. These 2 electrons will cross the sign here, and then it becomes plus 2 electrons. It's the same thing, okay? It's like an equation, a mathematical equation. Minus 2 electrons before this sign. When it crosses over, it becomes plus 2. Okay, it's the same thing, right? So we have 2 opposite processes that are happening here. By the cathode, we are gaining electrons. Okay, there is gain of electrons by the cathode, but by the anode there is loss of electrons. Okay, so if you are to link this topic to oxidation and reduction, okay, because whenever you are learning chemistry, yeah, just have concepts that link together in your head so that you can be in a position to understand what you are talking about, okay? Remember this, okay? All read, okay? The topic on oxidation and reduction, okay? Oxidation is loss of electrons. Reduction is gain of electrons, okay? So we can also say by the cathode, we actually have, okay, gain of electrons. So by the cathode, we are having reduction happening. Oxidation is loss of electrons, and by the anode, we are having, okay, oxidation happening. It's very important for you to not to isolate topics as you are covering chemistry. Some of these topics are interlinked, okay? So anodic reaction can also be called oxidation, and cathodic reaction can also be called reduction, because the ion here is actually going to be gaining electrons. That's reduction. And then the bromide ion here is going to lose the electrons, and that becomes oxidation. So at the end of the day, what are we going to observe? Okay, by the anode, okay, we're going to produce bromine gas. So you actually see bubbles here, brownish, reddish, okay, bubbles of bromine being generated. And by the cathode, the whole cathode or part of it is going to be coated with a grayish metal, because we are generating lead metals there. So what have we done in essence? Okay, what we have simply done is we started off with our our lead bromide, which was liquid, and at the end of the day we ended up with lead solid, okay, and bromine gas, okay, and as a result we are having some form of decomposition there happening. Okay, we have split lead to bromide into its constituent substances that made it up, and as a result we split it up. It was a splitting, it was lysis, but this was facilitated by electrolysis, by electricity, and as a result we call it electrolysis. So this is a summary for electrolysis of molten lead to bromide. It's very, very simple, straightforward, as long as you are dealing with molten substances. When you are dealing with aqueous substances, again, we have to write ions present, and then we have to deal with selective discharge. Okay, this was our session today, students, electrolysis of molten lead to bromide. If you like this video, please subscribe to my channel and also share with your friends. Also show by thumb up whether you like this video, and use it for your preparation for exams. And it is my hope that you use this previous video and also this one. A combination of these two videos will be in a position to help you to appreciate what is this process of electrolysis. But remember, when you are covering this topic, stick to your syllabus. One of these concepts will be covered in the core section, and the other one will be covered in the extended or the supplement column of your syllabus. Make sure that you are not extending when you are not supposed to extend. Thank you. Bye for now.